Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. Today we are going to continue and finish the part on the data definition with SQL. And then we will have again a mathematical part with the relational algebra. But before we start, I would like to ask you a question. And I need to click right here. If it lets me, yeah. So which one of the following does not characterize a collection as a table, right? We define collections and then we said they have to fulfill a few things. And then we can say that these are tables. So which ones of the following does not characterize a collection as a table? Relational integrity, atomic integrity, attribute integrity, or domain integrity? You should be a co-host. Yeah. So far, everybody agrees. All right, so let's settle on that one, right? So indeed, relational integrity means that we have the same support, so every record has the same attributes. Then atomic integrity means we have only atomic values. We don't have tables in tables in tables in tables. We don't have objects, dictionaries, lists, arrays, anything like that. We only have atomic values. Domain integrity means that in the same column, all the values have the same type, integer, date. And attribute integrity, I just made that up. There is absolutely zero reason why you would want to restrict the attributes of a table to have the same length. I mean, there could be reasons in specific cases, but not in the general design of a relational table. All right, that's great. So let's move on to the next one. I also need to click right here. What is a relational table? Is it a relation in the mathematical sense over attribute domains? Or is it a mathematical relation over several sets of attributes? Or is it a set of relations between strings and values with monotonous support? Or is it a set of maps from strings to values that additionally fulfills relational, atomic, and domain integrity? We have two competing answers. Three. All right. In fact, there are two correct answers. So the majority is correct about sets of maps from strings to values, plus the three constraints that I told you about. The first one on a mathematical relation over atomic attribute domains is correct too. This is in fact the original and textbook definition of a relational table, right? And as I said, it has a few drawbacks, like in that one, for example, the attributes, the order of the attributes would actually matter when you have a mathematical relation. So there's a few things like that, but this actually gave the name to relational table, right? So the first and the fourth answers are correct. The second one doesn't make sense because it's not about the sets of attributes. Over the sets of attributes that we have relations, it's over the domains. And the third one also doesn't make sense. I totally made up monotonous support. And we don't define relations between strings and values, but again, between domains, if you want to have relations. Okay, so vast majority is correct. Then we can continue. So this is where I left you. I explained that PostgreSQL, in fact, can break the rules. In particular, it can break relational integrity. in the sense that you could omit some values. So technically that would break relational integrity, but it allows you to do that. But if you really, really want to enforce relational integrity and you don't want any missing values anywhere, then you can do this by adding not null, not null, not null, not null to every single attribute in your schema, and then you know that it's not going to be broken. In some cases, in real life, you might want to allow for nulls, and that's fine. Then it's the default. Who remembers that? Right, that we did last week. But there's many other ways you can actually put constraints, further constraints on the tables. I will show you. But before we do that, I wanted to show you how, after inserting the data, you might want to modify it. Right? For example, you added all of the characters of Star Trek, and you want to modify the family name. So last name, set it to Picard instead of Crusher. You can do that, and that has the effect that after that the table has been modified. Right. So this is the effect of an update, and this is the syntax for it. Where is called a where clause, and last name equals Crusher is a predicate. It selects the records that you want to modify. We'll see that it's also going to be used in 2 weeks for other things in SQL, right? But we'll see first the relational algebra. So who understands that query? Very good. So that's to update the value of a tuple. What if you want to delete a tuple? Well, you can do that too, also with this where predicate. Delete from persons, where the first name is Spock, and that modifies the table. You used to have 3 records before, and now you have 2 records left because exactly one of them matched the where clause. Okay? It could be several, right? But in that case, it's just one. So we can remove tuples. The next feature I want to show you in SQL is if you would like to enforce relational integrity, so you don't want the nulls to be there. The nulls are missing values, remember. But instead, you want to fill the missing values with default values. So you want to give the flexibility to the users to insert tuples with missing values, but instead of putting a null for the missing value, you would like to put some default value. So here, let's say the middle initial default value is n, and the last name default value is none as a string. It's not a null, that's the string none. Then now I can insert these two, this tuple Spock 22300106 true, but you notice that there are only 3 values in here, while there are 5 attributes in there, and we specify which ones: the first name, the birth date, and the scientist. So we have these missing values here in the record we want to insert. But this time, it's not going to put nulls in there. It's going to use the default values that I defined, right? So here I said default n for middle initial, so it's going to put an n. And I said default none for last name, so it's going to put none. Who is with me? Right? All right, so these are the default values. And by default, so the default is null, right? So if you don't specify a default value, then it's going to be putting nulls when the values are missing. All right, so that's pretty much it. Now, what if you want to modify tables? So here, I don't mean just modify the records like I showed you with the update and the delete, but modify the schema of a table, the columns, the types, and so on. Right. So if you want to remove a column, you want to modify the constraints on a column, maybe even the type of a column. That might be tricky though. All right, so first, let's say I want to add a column. So on the left here, you have the original table with 1 attribute and 2 records. And I want to change that table by adding a column whose name is flag and of type Boolean. So how many columns do I have after that? Who says 1? Who says 2? Who says 3? All right, so 2 is the majority. That should be an easy one. So indeed, we add that column. but we are adding a column to a table that already has records, right? So if it's empty, that would be easy, right? It's just a new schema. But here we already have records, and these records must normally have values. But since you're adding a column, then of course they don't have values. But this is fine, you can just fill them with nulls, right? Again, it's always what you do when you don't have values, you just put a null. And technically, it breaks, again, relational integrity because these two records wouldn't have a flag value. But this is fine because here, you don't restrict it to be not null. It's just written flag Boolean, so it's allowing nulls. So it's totally fine to add these two nulls in there, right? If you're not happy with the nulls, you can also specify a default. So you say flag to Boolean default true. And then that now makes it 3 columns because I added a third column. The default is true. So now instead of putting nulls in there, it's going to put true in there. Who is with me? All right. The syntax right here that you see here with the name, the type, default true, and so on, right here is exactly the same syntax as you have. Let me show you on your schemas. That's exactly the same syntax as here, where you have the name, the type, and all the constraints. Exactly the same syntax, right? So when after the add colon, that shouldn't be surprising, exactly this order right here. It's the same as in create table. Okay, now you might want to say not null, right? So what if I want to add yet another column, integer, and I say not null? What do you think is going to happen? Who thinks it's going to work? Who thinks it's going to be an error? Yes, you're completely right about this. You can't do this because you wouldn't know what to put in there, right? You don't allow the nulls. You don't have any default value, so there is nothing you can put in there. So that's an error. But what can you do if you still want to keep the not null and not make it an error? You could add a default value, exactly like this, default 42, of course. And now you have a succeeding update. Okay? So not null default 42 is going to fill them with 42. All right. Now you can rename columns. Yes, we have a question. That's a good question. I think it probably doesn't. We will try during the break. We'll tell you. I think it shouldn't matter. I don't see why there should be any order, but we'll check. Right? That's an easy thing to do. All right. So can you maybe please make a note of that so that we don't forget? All right. And also I want to say, because there's not been a lot of questions on Zoom, but on Zoom you can ask all the questions you want. All you need to do is write them in the chat, and Marcin, who is here, is going to read them for you. So there is nothing to be afraid about. You can ask all the questions you want in the Zoom chat. Right? We won't ask you to speak over the microphone or anything. So there's nothing to worry about. Yeah. Oh, yes, I need to repeat them. Thank you for reminding, because in this room, we don't have a microphone for, I don't think there is any microphone. Yeah, so that's a very good point. So let me repeat the last question that was asked is, when we have this not null and default, is there an order in there? Can we put default 42 and then not null? Can we swap that? And so we said we are going to verify. I think it should not matter, but we'll verify that. Thank you very much for reminding me of that. And whenever I forget to repeat a question in the lecture hall, people on Zoom, please interrupt me and ask me to do it. You should not hesitate to do that, right? Okay. So yeah, the next thing we can do is rename columns. So if I'm not happy that it's called flag, then I can just call it F. And all I need to do is rename column instead of, it was add column, but now we say rename column, and we just rename it to F. So it's exactly the same table, we just change the name, right? But the alter table followed by the name, that's always the same. Okay, that should be easy, right? Right now. Who finds it easy, all of this? Right? It's very visual. We just modify stuff in the table. So, okay, very good. Now you can also delete a column, and it's as easy as drop column, right? Drop column F. How many attributes do I have left then? Who says 1? Okay, great. Very good. So we dropped the colon. All of these are actual changes. I have a table and we modify that table in place. And then the table looks different, right? These are really changes, updates that we make in the system that changes the state of the table. We call it a side effect in computer science when things change. It's very important because in the relational algebra, that's going to be different. It's not changes, it's computations. But here it's really changes. We really modify. If you try to look at the table after that, you will see that it has changed. Okay. And then, of course, if I'm not happy with the name of the table, then I can also change that name. So now if I don't like Hello World table, I can just rename it to table or whichever name you want. Okay. Okay, so that was an easy part. The next thing that I would like to show you is that in addition to not null and default, there's other things that you can do. So these are called consistency constraints, and they go beyond relational, atomic, and domain integrity. So you can do even more than that. So not null you already know, but there is also check and unique that I will show you. So okay, so not null you already know. So that's just a repetition of this. So you can add not null, and if you don't put anything, then it's allowing null by default. Right. So for example, if you say text not null, then this is going to be an error. That's not possible. It will not let you do that. But here it would be perfectly fine. Okay, now check. Check is an additional constraint that you have on the values that can be in a certain column. For example, you might want to just make things up, right, that don't make sense, but you might want to say the name cannot be Spock, right? This smaller than, greater than is just a sign for difference than. There's another one is with exclamation mark equals. It's just a matter of convention in different languages. But anyway, here, with this, you just say the name cannot be Spock. You're disallowing it. So it means that the first record here would be valid, right? This record would be valid because the name is not Spock. So this is true. But here, the name is Spock. So Spock is not Spock, right? So you do, so that would be forbidden. And then you wouldn't be able to do that, right? I was just wondering the same thing as I was saying it. We could actually try. Do you have a working Jupyter notebook, or maybe you could start it, and then during the lecture we can actually play with it. So if you start it, then I come back to you in a few minutes, and we'll try both the default swap with not null and then the different than sign. Okay. So this is the same thing, right? You can either put the check after the attributes that you're checking, or you can put it at the end. That's the same thing. The difference is that here, if you put it in there, this is called the colon constraint, because you're specifically restricting that colon. Here, that would be a table constraint that restricts the whole table. The benefit of a table constraint, because you might ask, why do we have the choice if that's the same thing? But actually, it's not exactly the same thing, because when you have a table constraint like this, you can write constraints that involve multiple columns. For example, you might want to say that whatever, for one record, whatever is in A must be strictly greater than whatever is in B. So here, for example, that would fulfill the constraint, check A strictly greater than B, but here you agree it wouldn't. Right, so that would be an error, and you would not be able to put these records in the table. Who is with me? Right, okay, so this is check. You can give them names. It's just like your pets, right? You give your names and your dog's names. So you can also give the constraint a name. It can be useful because when you get an error message, because the constraint is not fulfilled, then the error message will give you the name of the constraint that is not fulfilled. So it can be, if you have a lot of constraints, that can be helpful to give them names. Okay, so that's how to name a constraint. Okay, so that was the check constraint. And now we move on to the unique constraints. The unique constraints enforces that within the same column, the values must not repeat. They have to be unique. So for example, if now you have two Spocks, you have a clone, then Spock, Spock, now it would break this constraint here because name must be unique. If you don't have the constraint, it's perfectly fine to repeat values, right? There's nothing wrong with that. But if you, that's strange. Yeah, there was maybe a CPU overload. So here, that would be forbidden with the unique constraint, right? Note that if you didn't have the constraint, it wouldn't contradict the set of maps semantics, right? Because you would still have distinct values, right? So, but here you ask it to be unique. Students, you don't mind. So actually the two truths are fine, and AHFAO unique. Here too, you see 23, 24, 25, they're all unique. So this is fulfilled. Yes? Very good question. For null, I can tell you because I have a slide just right here. Maybe so let me answer your question in 10 seconds after I've shown the next two, and then I'll come back to that. So just like check, the unique can be a colon constraint, like in here, or it can be a table constraint, right? So you can put unique name and unique AHFAO like this. And now a question that also usually comes up is, what about forbidding unique, non-unique combinations across two columns, right? So for example, if you say unique name AHFAO, what you're forbidding here is that you cannot have two records that have at the same time the same name and the same social security number, the same AHFAO. So in that case, you see that the table here passes the validation because name and AHFAO is always unique. There's foobar null, there's spock true, there's foobar 24, spock 24, and spock 25. That's every time a different combination. So it passes the validation. Who agrees? Right? Who agrees? It would not have passed the validation of just unique name or just unique AHFAO. Right? Very good. Because you see there's a double spock and there's a double 24. Right? So you see the difference between this, where it's individually checking for uniqueness within columns, and here where it's jointly checking for the uniqueness over multiple columns, right? And that you can do either as a column constraint or a table constraint, but this you can only do as a table constraint because you involve multiple columns in there. Now, your question. If you put a unique in there, it will complain if non-null values repeats, but if you have multiple nulls, it's not going to complain because null is really special. So it's a missing value, it's not there. And this right here is not going to break the constraint, right? But maybe you're not happy with that. Maybe you want to change that behavior. Maybe you also don't want to have twice a null, right? But in that case, all you need to do is just you add nulls not distinct, and now you're forbidding this, right? So this is something you can control. With default values, I can guess that the default values must also be unique, but we also need to check. If you can add that, Marcin, maybe to the list of things that we would check. Right? I don't know if the default values, I would think they would behave just like any other values, but we will check that as well. Okay? Who is still with me? All right, very good. So we're moving on to the next cool feature, primary keys. So on primary keys, there's a whole theory that will require 2 weeks of lectures to explain all the math behind primary keys and so on. But on the very high level, it's very easy to understand what a primary key is, right? And I'll do the theory later on how to find them. So a primary key is basically a column or multiple columns that uniquely identify a record. For example, in Switzerland, the social security number uniquely identifies a person, right? So you can use, if you have a table of people, then you can consider that the AHFAO column is a primary key. Now, so this is the point of it. You could, for example, if you want to identify an insurance contract, I was about to say identify a car, but more exactly identify an insurance contract, then you need 2 columns, the content and then the number of the license plate, right? That would be two columns that jointly identify the car. The canton is not enough, obviously, but the number is also not enough. You need both the canton, the two letters, plus the digits. But I said it identifies the contract and not the car because I think in Switzerland you can move them on different cars. So this is why I need to be careful when I say that. Okay, so now what does it mean to uniquely identify a row? Then basically, what it means is that it can't be null, because that wouldn't make sense to identify something with nothing, right? So it can't be null. And it must be unique. You cannot have two persons with the same social security number. But then you might tell me, well, if all we want is that it's not null and it's unique, we already know how to do that. We can just put unique, not null, and we are done, right? You agree with that? And yes, and you would be correct that in terms of constraint, that would actually enforce the constraint. But in fact, so that's an example, right? Where it fulfills, it's unique, it's not null, and so on. But on primary keys, there's something else that is important and that I will also explain today. When you have a primary key that uniquely identifies a record, you want to use that primary key to find the record as a reference to the record. And so this is why we need to explicitly say primary key to do that. And I'll show you later how to reference. We have a question over there. Where is the primary key always? It's always a colon, the primary key. In that case, the alpha colon. Maybe I misunderstood your question. Do you want to ask during the break? Or? Yeah, all right. So come to me during the break, and then we'll talk about that, right? So to recap, to be clear, whenever you have, so I put them in green right here. Whenever I write something in green right here on the same line as an attribute or a column, that's called the colon constraint. It's a constraint on the column. And whenever it's written at the end, that would be a table constraint. So here, that would be as a table constraint. And here, that would be as a primary key over multiple columns, right? So of course, in life, that's not how it happens, right? But assuming for a moment that the first name and the last name of a person uniquely identify that person, then we would write primary key first, last, right? In real life, you shouldn't do that because that's not the case. You have multiple people that might have the same first and last name. It's only an example, right? Okay. For example, the DOI, yes, absolutely. If you want to identify publications, then the DOI would be a very appropriate primary key for this. And actually, the way you can see it's a primary key is that you can even put them as link on a page and click on it, and then you get to the paper, right? So that's exactly the notion of reference, right? And you dereference the DOI by clicking on it, and it goes to the page. Yeah, so that's a very good example too. The course unit numbers at ETH are also identifiers for the course units. Your Leggy number also identifies you as a student at ETH. There are many, many other examples like this of primary keys. Right? So as a colon constraint, as a table constraint, but then you need to specify the colon, or as multiple columns, right? So you see that you have this idea that whenever you have either primary key or check or unique, anything that involves multiple columns, then you must put it at the end. It has to be there at the end. Okay, and we'll come back on you. So during the break, regarding your question on the scope of the primary key. All right. Okay. Now, when I said a primary key also means you can reference it, I would like to show you how you can reference a primary key, and that's called the foreign key. A foreign key references a primary key, usually. So, as an example, I'm just using the tax office, right? So the tax office has people in their databases and they have their fiscal residence, let's say. And so If they have the fiscal residence of a few people, then they identify them with the AHFA, with the social security number, 23, 24, 26, saying like whoever has the number 23 is a Swiss resident, 24 is an Austria resident, and 26 is a UK resident. And the way it works is that this social security number actually references a table with people. So it means in that table, you just have the social security number, but you don't know who that is, right? So if you want to know who that is, then you need to look it up in this other table, persons. It's a different table that has, with every social security number, their names, right? Okay. And now what you can see several things. So first, this, which we defined before, is a primary key. So this AHFA is a primary key in that table, uniquely identifies a record. So they're all unique in there, there's no nulls. Here we see that this one succeeds, so 24 actually has a match, 23 has a match right here, and this one doesn't have a match, right? So because it doesn't have a match, it actually fails the foreign key constraint, right? Because when we have a foreign key, we really want the foreign key to correctly reference a primary key, right? Who agrees? Okay, very good. So that's useful to have a foreign key constraint to make sure that whenever you reference a person by social security number, that person actually exists. That social security number actually exists. So this is how you do it, how you define a foreign key. It's again a constraint, so I put it in green after a colon, as a colon constraint. So I'm saying now that in that table with the fiscal residence, the social security, AHFA, references in the table person specifically the colon AHFA, right? You can put actually any colon in there, it just must be unique. That's what you need. But of course, if it's the primary key, it's even better. And in fact, it's so better that if you mean the primary key, you don't even need to specify, because there can only be one primary key, possibly multiple colons, but it has to be exactly at most one primary key. So if you just say references persons, then that is going to specifically reference the primary key in that table, right? If the primary key is not defined, then of course you cannot do that. So that would be an error, okay? But if you are not happy with the primary key and there is something else that is unique in the table, then you can still specify it and overwrite it. Okay? Yeah, so that would be totally allowed, right? You might have, when you have a foreign key, you might have duplicates. That's totally fine. That would be an example of a person who is a double resident, both in the UK and in the US, and then it appears twice. The only thing that must be unique is in the reference table, in the person's table. The social security number must be unique. But in the table that references the other table, then you can have duplicates. That is perfectly fine, right? For whom does that make sense? Right? Very good. The same goes, let's say you're at ETH, you're taking a course unit. In the database, in the ETH database, there's probably a table with the student leggy number associated with the course units that they are taking. And you agree that if you're taking multiple courses, then you will appear multiple times in this table with which courses people visit. You will appear multiple times with each one of the course units that you're visiting. And the course units will, of course, appear multiple times because there's more than one student in most classes. But in the table that lists the people, then you're unique. Then the leggy number is unique in the people table. And in the course units table, that would also be unique, right? Okay. You can also have compound keys. What if I take again my very bad example where first name and last name identify a person? Again, it's made up, but that's just for my example. You can also think of the content and number for the license plate if you prefer. How do you do this? Well, you cannot do it as a colon constraint because in a colon constraint, you can only specify one colon, right? So it has to be a table constraint. And so as a table constraint, you say foreign key, first, last. These are the two columns that you want here to reference. Reference is the table person, first and last, you specify, and these two jointly must be unique, right? Or they can be the primary key, and if they are the primary key, then you don't need even to cite them. Okay. The next thing is that when you have a foreign key, it can perfectly be null. Right? It's not a primary key. In a primary key, you cannot have null, but in a foreign key, you can absolutely have null. Right? So here, you would basically have a course called formulas that is just not assigned. Right? It's not assigned to anybody, and that's perfectly fine with the integrity constraint because it's only when it is assigned that it has to match somebody. Right? Okay, so the nulls would be allowed. If you do not want the nulls, what can you do? If you're not happy with allowing nulls? Not null, exactly. You just add not null, and then you don't have any nulls, right? So it's like a Lego game. You can basically compose your own constraints. Okay. All right. Then I want to show you one issue that can happen when you delete stuff and you have foreign keys, bad things that can happen and how to prevent them. Imagine that we have this table somewhere with all the people, like the table of all students at ETH or the table of all lecturers or here all the researchers or people. And I delete an entry in here, I delete a record. But do you see that that record might actually be referenced from somewhere? So do you see that if I just don't think and just go ahead and delete the record, then this table right there will no longer fulfill my foreign key constraints because now it has an invalid reference that would not be in the table persons. Who sees that? Right? So basically, whenever you delete a record, there's always the risk that it's referenced from somewhere else. So it means that whenever you introduce the reference, you need to tell PostgreSQL what to do with that when that happens in order to make sure that we guarantee at all times the constraint. So PostgreSQL guarantees you the constraint. You just need to tell it how to do it. So what do we do? The first thing you could do is cascade. Right? For example, a student successfully graduates from ETH, is removed from the database of matriculated students. On delete cascade means that if they are registered for any course, you just also delete all the referencing records. That's called cascading delete. If it's referenced from 10 other tables as foreign keys and maybe with 1,000 records, then they will all get deleted in cascade. Right? That's the first thing you could do to automatically delete in cascade. The second thing you could do is just say, if I ever do that, I want an error. I don't want to delete anything. I just want to give me an error if that happens. So if you say on delete restrict, so on delete cascade would be the first one, on delete restrict, then if you try to delete, it just says no, can't do that. There's foreign keys pointing to that record, and you told me to not allow that, so you cannot delete that record. If you want to delete that record, you first need to delete the records that reference it, and then you can delete that record. Okay? That's the second thing you can do. There's others that you can do. The third one is, wow, need to be closer. Oh, there. Oh, it's jumped too far in the future now. Okay. The third thing you can do is set them to null. So if you delete this code Gödel and so on, then wherever it was referenced, the reference is changed to null, which is perfectly fine because we saw that you can absolutely have nulls and that doesn't break the foreign key constraints. And the last thing, set to default. So if you happen to have a default for the column, so let's say the default for first was Albert and the default for last was Einstein. Of course, it's totally made up because nobody would actually do that in a real-life database. But as an example, if that was defined as the default, then this is going to just replace Kurt Gödel with the default values in there. Who understood everything? Oh, who understood almost everything? Okay, very good. Do I have that? Yeah. Oh, I can actually check. I'm silly. I have the question right there. So tell me where you are. Is it activated or something? Or you need to maybe the time to connect to it? That's strange. Did anybody actually answer and it just doesn't show, or is it just that it needs time? Ah, so I'm not sure what exactly, it's not showing the right question. Okay. Well, I try to fix it. Is it the same code as earlier? Let me check. Yeah. It's in volume. Yeah. So that's, yeah. Let me see if there's anything I can do in there. Yeah, it's the first time that I use this technology this year. So it's very strange that it now it shows it. Yeah. All right. Then I can project again. Oh yes. Now I can see the. Let me project it again. Just need to click on other places every time I reactivate the okay. Very good. And now the speed is totally okay. So that's your opportunity to accelerate me, slow me down on the lecture. Okay, awesome. Some of you are below 80%, not a problem at all. That's totally fine. So what I recommend is, so first you can rewatch the recording, or you can, of course, you should everybody read the textbook, the chapters of the book. But of course, and more importantly, you can send a message to the Moodle forum. You can send the TAs an email. You can send me an email and ask anything that is not clear to you. This is what we're here for, so you should not hesitate, right? It's a university. We are here to learn. And there is no such thing as a stupid question. So anything you don't understand, anything that wasn't clear, that you need re-explained, maybe in a different way, just reach out. And of course, you'll have the exercises because the best way, you know, that's a practical lecture. So the best way to learn that is to really download the Docker file, run the command, open your Jupyter notebook, and play with it. Like write queries, try stuff, experiments. That's really the best way to get acquainted, right? Like you can really then touch the tables and manipulate them, modify the schemas, try things out. So that's what I highly recommend. Who actually reads the textbook? You should, right? The library, the ETH library has copies. I heard that there might be copies on the internet, but I'm not allowed to point to any of them because I'm not sure if they're supposed to be there. But normally you should go to the ETH library and get it. You can also buy it if you want. But there's the ETH library right in this building. There is the computer science library also that has copies, right? So I really recommend that you read the book. Yes?